Hello, welcome back. This is Differential Equations by Dr. Oz. In this video, we have a perfect application of first order differential equations. In this example, we're provided a bacteria culture having an initial population of p sub 0, and the bacteria population is growing in time, and the rate of growth is proportional to the number of bacteria present at the time t. And this is a good model fitting into our first order linear models, specifically of the form dx over dt equals k times x. And as you see that, the rate of change of x in time is proportional to x itself by the constant of proportionality k, and we are provided an initial condition. And in fact, we know how to solve this type of initial value problem. So in our particular case, we have one measurement done after 1 hour, and the population is measured to be 3/2 of the initial population. And for the rest of the video, we're going to try to find the amount of time necessary for the number of bacteria population to triple. So it's going to be essentially 3 times p sub 0. All right, let's get started. All right, I split the question statement into 3 parts. In the first part, we are given 2 measurements of the bacteria culture at different time moments. In fact, one is the initial time moment, which is t equals 0, and the other one is like t equals 1 hour. All right, let's start with the second statement. So we're given that p of t representing the number of bacteria at any time t, and we also stated that the rate of growth is proportional to p of t. So rate of growth means like rate of change of the population in time, and in mathematics it's the first derivative of p, and that is equal to constant of proportionality times p. Okay, so now we have the differential equation model. And now let's go back to the first statement. In the first statement, we're given the initial bacteria population. So that essentially means that p at time t equals 0 is equal to p sub 0. We are also given the population at time t equals 1 hour. So that is in fact p of 1, which is equal to 3/2 p sub 0. So staring at what we have found so far, we have 2 unknowns, k and p sub 0. All right, now let's stare at the last statement. We're going to find the time necessary for the number of bacteria to triple. So initially we have the population p sub 0, and we want it to be 3 times p sub 0. So therefore, I'm going to find the time moment for which p of t is equal to 3 times p0. And here, t is what I am trying to come up with. All right, let's first solve the differential equation. And this is a linear differential equation. We can use the integrating factor idea, but we can also use the separation of variables. In fact, if we divide both sides by p and multiply by dt, we have the equivalent formulation dp over p equals k times dt. And now the variables are completely separated, so we can integrate both sides simultaneously. So the first integral provides us ln absolute value of p, and the right-hand side is k times t plus c. All right, from here, absolute value of p is equal to e to the kt plus c. Let's try to simplify this a little bit more. Well, first off, exponential functions are always positive, so we don't need to carry forward the absolute value. And we also know that e to the kt plus c can be written as e to the kt times e to the c. So here, c is an integrating constant, so why don't we relabel that as c, so that the solution p of t is c times e to the kt. All right, we have the bacteria population is known at any time up to the unknowns c and k. So why don't we use the conditions coming from the first statement. So p of 0 is equal to p sub 0, and p of 1 is 3/2 of p sub 0. So let's use these two conditions. So p at 0 means you have c times e to the k 0, which is c, equals p sub 0. So in fact, c is the initial population. And we also have p of 1, which is c times e to the k. That is equal to 3/2 of p sub 0. But since c equals p sub 0, we can divide both sides by p sub 0. And we're assuming that we have a population non-zero in the beginning. So we can divide them out so that e to the k is 3/2. All right, to determine k, we're going to take the ln of both sides. So ln e to the k is just equal to k times ln e, which is just k. And the right-hand side is ln 3/2. And this is approximately equal to 0.405 and 5. All right, so we have C determined, we have K determined, so we can rewrite the description of the bacteria population at any time t as P sub 0 e to the 0.4055 times t. All right, so now we can go back to the last statement. We're going to try to find t, for which p of t equals 3 times p sub 0. All right, why don't we set this to 3 times p sub 0. So to find t, first, let's divide both sides of the equation by p sub 0. So these guys are divided out. So we have e to the 0.4055t equals 3. So if we take the ln of both sides, we have 0.4055t equals ln 3. All right, so now let's divide both sides of the equation by 0.4055, so that t becomes ln 3 divided by 0.4055, which is approximately equal to 2.71 hours. All right, to sum up, we had the initial population p sub 0, and the growth is represented by this exponential model. And after 2.71 hours, the population triples as seen in the picture. All right, that's the end of the video. Thanks for watching. I'll see you in another video. Bye.